This is Jyoti Sharma taking the lectures on the subject Basic Electrical Engineering, and the topic is electrical machines. I have taken one of the lecture regarding DC machines. In that we have discussed the construction of the DC machine, let it be generator or a motor. Then we have also gone for the EMF equation of DC generator. Now coming to the second lecture, the contents would be the numericals which are based on the EMF equation, then the types of DC generator and their voltage equations, then the voltage build up in self-excited DC generator, right. Now going for the very first example, likewise a 4-pole generator having wave wound armature winding has 51 slots, each slot containing 20 conductors. What will be the voltage generated in the machine when driven at 1100 rpm, assuming the flux per pole to be 7 milliweber, right. So what are the given data we are having is the number of poles for the generator is 4. It is a wave wound armature having 51 slots, and in each slots we are having 20 conductors, right. So we want to have the voltage generated. We know that the EMF equation what we have derived in the previous lecture, that is given by phi p n z by 60A, where phi is the flux per pole, z is the total number of armature conductors, n is the speed of the armature given in rpm, p is the number of poles, and a is the number of parallel paths, right, in a generator, in armature winding. Now obviously the number of parallel paths, that depends upon whether the armature is wave wound or whether it is lap wound. So for a lap wound, we know that for a lap wound armature, the number of parallel paths is always equal to the number of poles, right. And for a wave wound armature, if it is a wave wound armature, the number of parallel paths is equals to 2. We have seen that, right. The number of here the generator is wave wound, right. So the EMF generated equation phi p n z by 60A, the flux which has been given to us is 7 milliweber, that is flux per pole. Number of conductors, right, for that the information given to us is we are having 51 slots in the armature winding and each slot is having 20 conductors. So the total number of conductors becomes 51 into 20, that is 1120 conductors, right. Now number of parallel paths is equals to 4, or is the number of poles is equals to 4, the number of parallel paths is equals to 2, as it is a wave wound generator, right. And the speed which is given to us is 1500 rpm, right. So the equation, so just substituting the value for phi p n z by 60A, will be having the EMF induced as 357 volts. Moving on to another example, say a 4-pole generator with the wave wound armature has 51 slots, each having 24 conductors. The flux per pole is 10 milliweber. At what speed must the armature rotate to give an induced EMF of 0.24 kilovolt? What will be the voltage developed if the winding is lap connected and the armature rotates at the same speed, right? So here both the things have been asked, right? So if we just go with the given data, the number of poles is 4, the number of conductors per slot is 24, and likewise we used to have how many slots? That is 51, right? So the flux that is given by 10 milliweber. Total number of conductors would be obviously 51 slots. Each slot is having 24 conductors, so that is 1224 conductors. It is once again a wave wound armature, so the number of parallel paths would be equal to 2. So from the EMF equation phi p n z by 60A, the speed would be coming out to be 588.23 rpm, right. Now the second question is what will be the voltage developed if the winding is lap connected and the armature rotates at the same speed, right. So now if the armature rotates at the same speed of 588.23 and the winding has been replaced with the lap connected, in that case what is going to be the induced EMF? So obviously The induced EMF expression, rest of the things are remaining same, the number of poles, the flux, the conductors, the speed what we have got, that is 588.23 divided by 60A. So the parameter which is going to get changed over here is A. Now in case of lap winding, we know that the number of parallel paths is always equal to the number of poles, which is 4. So just substituting this 60 into A as 60 into 4, the EMF induced would be 0.119 or 0.2 kV. Obviously, it will be the half of what we have got in the earlier case. It was 0.24, right? So in this case, as the denominator is now 4, it will be halved. So it is now 0.2 kV. Now going for the another example, a 4-pole lap wound DC generator has 42 coils with 8 turns per coil. It is driven at 1120 rpm. If the useful flux per pole is 21 milliweber, calculate the generated EMF. Find the speed at which it is to be driven to generate the same EMF as calculated above with the wave wound armature. The numerical is very much similar, but in this case, the EMF generated is the same and we need to find the speed in the another case. When earlier it was lap connected, this time the second case is it is wave connected. So once again, going with the given data. Now this time, the number of, we are having for the number of, total number of conductors, we are having 42 coils. And in each coil, it is having 8 turns per coil. So that is 42 into 8. And each coil is having each turn is having 2 conductors, right? So that becomes 42 into 8 into 2. So we have just got that we are having 42 coils, 8 turns per coil, and once again 2 conductors per turn. So that is 42 into 8 into 2. That gives me 672. The number of poles is 4, speed is 1120, the flux is 21 milliweber. So, and again the number of parallel paths, because this is a lap wound, so it will be equal to the number of poles, that is 4, right? So the generated EMF would be 0.021 into 4 into 1120 into 0.6 into 672 divided by 60 into 4. So the induced EMF would be, or the generated EMF would be 263.42 volts. With the same second part of the numerical, now for a wave wound armature, right, what will be the speed if the same EMF is generated? So in the same expression, same equation, we need to find the speed, right, with the only changes this time it is a wave connected. So the number of parallel paths A this time is equals to 2. Instead, in the earlier case, it was 4. So just replacing this A with 2 and substituting for or finding for the speed, will be getting the expression as 560 rpm. So these are certain numerical based on the EMF equation. Now coming to the types of DC generators and their equations, right? Now in the earlier lectures, we have seen the construction of DC generator, the working of DC generator, how does the DC generator works. Likewise, we have seen the various parts of it, right? We have seen the field is being created by the field system, right? The armature is rotated with the help of certain prime mover, and thereby there used to be an induced EMF. The expression for that is given by 5 p Z by 60A. Actually, the EMF induced in the armature is actually of AC. The nature is the alternating or the sinusoidal, but by using the mechanical rectifier, that is the most important component of the generator, that is commutator, that internally developed AC is being converted to DC, and then with the help of the brushes and brushes assembly that supply, that voltage is being taken out for the external circuit, right? Now, what are the types of DC generator? So going with the DC generators, these are basically classified based on the way in which the field windings are excited, because these windings needs to be excited, these needs to be given supply. So the different types of DC generators are given by, it can be, broadly classifying, it can be a separately excited DC generator or it can be a self-excited DC generator. What do we exactly get with separately excited? Separately excited are those DC generators where the field winding are entirely separated from the armature circuit and they are being excited in a separate manner from the armature. They are no way related with the armature circuit, right? Whereas in case of the self-excited DC generator, these are in certain fashion connected to the armature circuit. So what are the various ways in which they can be connected? Depending upon that, once again, the self-excited DC generator is being once again classified into 3 categories. One is shunt, series, compound, right? Once again, we'll be individually seeing each of these generators, their voltage equations, how the windings are being connected. Once again, the compound generator, depending upon the constructional features, it can be once again divided into 2, that is long shunt or short shunt, right? Coming to the very first one, that is separately excited DC generator, right? So in this type of DC generator, the field windings, you can see these are excited from a separate source of supply, right? It has no connection with the armature circuit. The figure, it clearly shows the diagram for a separately excited DC generator. It can be seen here. The field winding is entirely separated from the armature circuit. It has been excited by a separate DC supply, right? Now, going with the relations, what will be the voltage equations for this, right? So, if you just see here that IF, if at all I say IF, this is the field current, right? IA, that is the armature current. IL, the load current, right? This is the armature circuit. The representation, the symbolic representation for a DC generator, that can be given by, it can be given by just the 2 most important things. One is the field, given by FFF, and another one, the armature with the brushes, right? It's a generator, induced EMF EG. The terminals are being noted as AAA, right? This is a symbolic representation for a DC generator. In a separately excited, obviously the field windings, these are separately excited by a DC supply. Field current, we have just seen. Now, what about the armature? Obviously, this armature is being connected to the external load. Then only I'll be having the load current, IL. It can be seen nicely that the armature current which I'll be having over here, this armature current would be equal to the load current in this particular circuit. So, the current relations holds good as IA is equals to IL, right? What about the voltage relations, right? That means the voltage relation between EG and V. What is V? V is the terminal voltage which is appearing across the load terminals, right? So, obviously, this time, what should be the relationship between EG and V? Obviously, the generated EMF must be equals to, according to the polarity, that must be equals to V plus the various drops which are occurring. What are the various drops? The drops which are occurring is the armature resistance drop given by IARA and the brush contact drop. This brush contact drop used to be a very small value, generally 1 volt per brush. So, these can be neglected in many of the numericals or while considering the voltage equation, but while giving it, we would definitely be considering. So, the complete equations become EG is equals to IARA plus V plus VR. That is brush contact drop. The power, what is the power developed in the DC generator? The EMF induced is EG and the armature current is IA. So, the power developed is EG into IA. And what is the power delivered to the load? That is V into IA, right? V, IA, because IA is equals to IL. So, that is given by V into IA. Now, self-excited DC generator, as we have discussed in a very brief, that a self-excited generator produces the DC output whose field windings are excited by the current produced by the generator itself. No separate source of excitation is being used for exciting the field, right? If that is so, now the question arises, then how does this self-excited DC generator produces the EMF generated, right? If there is no external separate source of field excitation, there will not be any field being created. If there is no field being created, you may be just making your armature to rotate with certain speed, there will not be any flux cut because you don't have any flux, but you really don't have any flux. Is that the case? No. So in this type of generator, some flux is already present in the poles due to the residual magnetism. We have studied in BH curves that the ferromagnetic materials are having the property of retentivity. That means when the external source of supply or the magnetizing force, magnetic field intensity, that is made zero, then also we used to have a small flux remaining in the poles, that is being called as residual magnetism. When the armature is rotated with that small residual flux, a small EMF and hence a small current is induced in the armature conductors. This current will produce more flux, which is in turn produces more current to flow through the field winding. This process will continue until the field current reaches its rated value. This complete process is being called as voltage built up in self-excited DC generator and can be given by a graph which can be drawn between the field current and the induced EMF, right? At the very starting, if at all I say, at the very starting, I don't have any field current. The field current is entirely zero. Why? Because I don't have any separate supply to get it excited. So until unless I get an armature current, I won't be having any field current, right? So there won't be any excitation. Okay, fine. At that very instant also, I'll be having a small flux, although I don't have any excitation because of the residual magnetism which is remaining in the magnetic circuit. I'm having a small residual flux remaining. Because of that small residual flux, when you make the armature to rotate, I'll be having the flux cut. Once there is a flux cut, I'll be having a small induced EMF because of that residual flux. Say this is the EMF generated due to residual magnetism, right? So I'll be having initially when IF is 0, I'll be having a small induced EMF, okay? Because of that small induced EMF, I'll be having, obviously, the armature circuit would be driving. I'll be having a small armature current. Because of that small armature current, I'll be having a small field current because of it. I'll be having a small current. I'll be having a small current, right? Now, because of this small current, obviously, I'll be having, once the current is increased, because of this increased current, I'll be having an increased value of flux cut. The field is now much more stronger. If the field is much more stronger, the armature conductors would be able to cut more flux, thereby increasing the flux induced, the EMF induced, right? Once again, when the EMF induced increases, once again, the armature current is much increased. When the armature current is increased, the field is much more stronger. The current will further increase. When the field current is further increased, it has more excitation. Armature, the induced EMF will further increase. And this process will continue, This will continue. And at one stage, this would be saturated. This is that saturated EMF, what you call it as rated EMF, generated EMF of the generator given by 5P and Z by 60A. Right? So this is the voltage build up in a self-excited DC generator. Now going for the classification for self-excited DC generator. So there are 3 types of self-excited DC generator based on the way in which the field coils and the armature are connected, and they are, we have seen, that is shunt, series or compound, right? Going for the very first one, that is DC shunt generator. It can be seen now in this type of DC generator, the field windings are connected across or in parallel with the armature. The shunt field winding are connected in parallel to the armature, right? Once again, the further circuit is the same. I'm having the load being connected to the externals of the armature circuit, right? Once again, what are the things to be known? ISH. ISH is the shunt field current, the current which is flowing in the shunt field winding, right? IA, the armature current, IL, the load current. So it can be very easily seen the relationship between the armature current and the IL and ISH. I must be knowing that IA is equals to IL plus ISH. Similarly, the shunt field current ISH, that can be given by the voltage across it is V, the resistance is RSH. What is RSH? It is the shunt field winding resistance. So that can be given by V upon RSH. Right. Once again, the terminal voltage equation, that is going to remain same. What is that? EG is equals to, once again, the terminal voltage V plus the drops. What are the drops I am having? IARA plus V brush, V contact drop. Right. So the equation is the same. Right. Now the power developed in the DC generator, that is once again the generator EMF is EG and the armature current is IA. So the power developed is EG into IA. The power delivered to the load, this time it is V into IL. Obviously, the power delivered to the load is always V into IL. But in the earlier case, for a separately excited, IA was equal to IL. So we have written there as V into IA. But in this case, I can't say that the armature current is equals to IL. Now, the armature current is equals to IL plus ISH, right? Now, in DC series generator, if at all I go with it, once again, it's a DC series field, series generator, as the name is suggesting. This time, the field windings are being wound in series with the armature, right? This can be seen. These are being wound in series with the armature, right? So now once again the same expressions. I'm having armature current. I'm having ISE as the series field winding current. IL the load current. It can be seen. It's a series circuit being formed. All the three currents would be same. So IL is equals to ISE is equals to IA. All the three currents would be same, right? Once again, if at all I say RSE is the series field winding resistance, right? Will the terminal voltage equation is going to remain same, right? Let's see, just it is a simple loop, right? If we just write the equation, I know that EG must be equals to terminal voltage plus the drops. And once again, what are the drops? The armature resistance drop, IARA. What is RA? RA is the resistance of the armature circuit plus one more drop this time. What is that? The series field winding resistance. So that is ISE RSE. Although I know that this time ISE is equals to IA, so I may even replace this ISE with IA, right? Plus the brush contact drop, VBR, right? Or terminal voltage equation, obviously I can give it as V is equals to EG minus these drops, IARA minus RSC minus VBR. Once again, the power developed is the same, EGIE. The power delivered to the load is V into IL. Now coming to DC compound generator, right? Now the DC compound generator has both the shunt field winding and the series field winding. One field winding is connected in series with the armature and another field winding is connected in parallel with the armature. That is why it is being called as compound, right? Based upon, the way of connection, how the parallel winding is or the shunt field winding is connected, it can be classified as long shunt or short shunt. Going with the long shunt DC generator, compound generator, in this case, the shunt field winding is connected in parallel with the combination of the series field winding and the armature. This shunt field winding is connected in parallel with the complete combination of the series field winding and the armature. This branch is larger. That's why the shunt branch is larger. That's why we used to call it as long shunt, right? So this is a long shunt DC compound generator. Once again, going with the relations, this is the armature. This is the armature armature current IA, right? Series field current ISE. You can be seeing that both the currents must be same. It's in the series. So one relation I'm getting is IA is equals to ISE, right? Is it equals to load current also? No, it can be seen, right? I'm having the shunt field current also and the load current also. So this must be equals to IL plus ISH, the load current plus the shunt field current, right? What about the voltage equation? Voltage equation, once again, it is same as that for the series. I'm having the armature resistance drop IARA. I'm having the shunt field, series field winding drop, that is ISC, RSC, EG, this is the terminal voltage V, and the voltage, the brush contact drop. Once again, so my EG must be given as V plus drops. What are the drops? IARA plus ISC, RSC plus V brush, right? So this is the voltage equation, right? Once again, the power developed is same, EG into IA, and the power developed V into IL. Now, in case of short shunt, what is happening now? Now the shunt field winding, as the name is suggesting, it is short shunt. So the shunt field winding is connected only across the armature. The series field winding is not again in the parallel with the shunt field winding as in case of the long shunt, right? So here now the conditions are a bit different. So if at all I just say IA is the armature current, ISH shunt field winding current, ISC series field winding current. So once again I'm getting the same relation that IA must be equals to, and IL is the load current also. So IL plus ISH, but this time IA is not equals to ISC as we used to get it in case of long shunt DC compound generator. Here, what is equals to ISC? IL is equals to ISC. You can see both of these are same. Do we have any change in the voltage equation as well? No, the circuit is the same, you just see. The loop is the same. I'm having the same generated EMF, I'm having the same terminal voltage, armature resistance drop, series field resistance drop, brush contact drop, right? So everything is same, so the equation is also going to remain same. So EG is given by V plus IARA plus ISC RSC plus VBR. Yeah. In case of long shunt compound generator, if at all I just say, how can I give the expression for ISH? Once again, you can see the voltage across the shunt field winding is V and the resistance of this is RSH. So that can be directly given. But what about in case of short shunt? Can I give once again ISH as V upon RSH? Is that the voltage across the shunt field winding? No. So what is that? If you just see this figure, so what is the voltage across? What is the voltage across the shunt field winding? It is either, if you just see, it is V plus ISC RSC. So when I want to give the expression for ISH, it has to be V plus ISC RSC upon RSH, right? Or I may give it in terms of EG. So that can be even given by EG minus IARA minus V brush upon RSH, both the ways, right? So this is how we can give the equation for the long shunt, short shunt, all the compound generators. Just going with an example, a shunt generator delivers 450 amperes at 230 volts and the resistance of the shunt field and the armature are 50 ohms and 0.03 ohms respectively. Calculate the generated EMF, right? So in this case, the generator circuit, that is very much visible to us. So the current through the shunt field winding, obviously we know that ISH would be given as V upon RSH. V is 230, shunt field resistance is 50, so the current is 4.6, right? So what about the load current? Load current is given as 450 ampere, right? So the armature current, that is given as IL plus ISH. IL is 450, ISH is 4.6. So the total armature current would be 454.6. Now the generated EMF expression, that is given by EG is equals to V plus IARA plus V brush. We don't have any information regarding the V brush, that's why we'll be neglecting this. This is although very small value, so we are neglecting that. So V plus IARA. V is already known to us, the terminal voltage is 230 plus IARA. What is IA? We have just found it out as IA is 454.6 and RA. What is RA? RA is 0.03. So 453 into 0.03 is 13.6, right? So the generated EMF is 230 plus 13.6, that is 243.6 volts. Going with another numerical quickly, a 4-pole long shunt lap wound compound generator delivers a load current of 50 amperes at 500 volts. The armature resistance is 0.03 ohms. The series field winding resistance is 0.04 ohms. Shunt field resistance is 200 ohms. The brush drop may be taken as 1 volt. So determine the EMF generated. Calculate also the number of conductors if the speed is 1200 rpm and the flux per pole is 0.02 Weber. Neglect the armature reaction, although what we are considering right now, the equations what we are considering right now, we are doing them by neglecting the armature reaction and armature reaction drops, right? Okay, so once again, the shunt field current can be given as obviously V upon RSH. So that is 500 upon 200, that is 2.5. Armature current is given by IL plus ISH, that is 50 plus ISH is 2.5, so that is 52.5. What will be the series field drop? ISC into RSC, and we know that here in this case ISC is equals to IA only, right? So in this case it is 52.5 into 0.04, that is 2.1. Armature resistance drop, once again the armature current into armature resistance, that is 0.03, so it is 1.575 volts. Brush drop, 1 volt per brush, assuming it to be having 2 brushes, so 2 volts. So the EMF equation, that is EG is equals to V plus IARA plus ISC RSC plus V brush. So this is V 500, IARA that is 1.575, ISC RSC that is 2.1, brush drop 2, I got it as 505.67. Now the second part is, we also want to know what will be the number of conductors in the armature, right? We also know that the generated EMF can be also given by the expression phi p nz by 60A, right? And we are having all sorts of information except the total number of conductors, just substituting that as 505.67. Number of conductors we need to find, flux we know, that is 0.02, speed we know, that is 1200 rpm, 60, number of poles P and A, number of parallel paths, it's a wave connected. So for a wave connected armature, once again the number of parallel paths is equals to number of poles, so that is 4. So number of conductors are appearing to be 1264. So this is all for today's lecture. We'll be continuing on with the DC motors and its various types and certain numericals on that in the next of the lecture. Thank you all.